Welcome to this module 2 of manufacturing systems technology. A brief review or recap of what we did in the last lecture. We talked about some basic definitions of manufacturing technology, also worked on manufacturing with a systems approach, how manufacturing systems would work with a core full of manufacturing processes. We talked about various consolidated models of a manufacturing enterprise, how different wings of a manufacturing enterprise can function with customer centric approach, where these wings can intercommunicate and also communicate with customers to have a good management of the whole enterprise activities. We also saw some of the aspects of what for example marketing as a very important tool and function can do to support an enterprise, where with a smooth flow of demand from the customer, it can always ensure that the harmony and the balance of the manufacturing system can be maintained. So it definitely plays a very key role with the time to time updation of what the customer thinking or philosophy is in terms of demand. The whole idea is to be able to give a smooth demand pattern to the remaining part of the enterprise, so that there are not many disbalances in the enterprise itself. So another very important aspect that any product which gets realized is basically the design of the product, and it is the design which actually is the starting process to map the customer thinking in terms of something which is a need or a want of a particular customer. So we will definitely like to have a historical perspective of how design can be done. Obviously nowadays product design involves very complex CAD tools, computer aided design tools, where there is a huge flexibility offered to the designer, to the product designer, to visualize whatever he thinks in terms of mapping of needs of a customer. And so we want to do a little bit of historical perspective of design, and as we have already seen, design and manufacturing formulate core activities for realizing a marketable and profit making system, okay, and therefore it is very important that design be done in an appropriate manner, so that not only from a standpoint of mapping needs of the customer, but also from a standpoint of giving a high quality product, design is a very important tool. In fact, there is a concept called robustness by design itself, which is the primary envisioning of the product capability of a system itself. And if robustness can be introduced at a primary level or an initial stage, then there can be a huge tolerance or variation that a product design can take in terms of the deviations of the manufacturing process, and still be able to manufacture the quality which is needed, okay. So that aspect is a very important aspect of any modern day manufacturing enterprise. So if you look at the figure here, which says the evolution of mechanical CAD CAM systems, you can see that there are various levels in which the design softwares which have enabled the designer hugely have emerged over different years, starting all the way from 1960 to the 1990s, okay. So definitely the computer aided design technology has emerged over the years to facilitate at least you can say the representation completeness of a design which is envisioned, okay. And without doing that, that's the first step. How do you do the engineering specifications, which would then get translated into exact product requirements or manufacturing process requirements, etc. So the first step obviously is a very good design, a flexible design package which can handle the various design issues related to the product design. So the first step in the history, if you look back in the 1960s, was the development of the two-dimensional drafting system, okay, which was extended to the three-dimensional models, principally initiated by something called a wireframe based design model. If when we are going to do CAD, we are going to address what exactly is a wireframe design, but it's actually a sort of a you can say pseudo three-dimensional representation of at least the edges of an object through which you can define the whole object. So however, it was not possible to represent the higher order geometry data, and particularly data related to surfaces, because when you are talking about edges you do not have any interconnectivity between the edges on a priori basis. It is just the representation of the edges in the wireframe model, but if there is an interconnect between such edges where there are exact location coordinates etc. which are specified, then the question of the surface mapping would come into picture. But here it is only the wireframe, and it is assumed that the person who is visualizing the wireframe model would be able to sort of map the surface on his own without the CAD package going into the great details of how the surface topology is going to vary between the edges. Okay. So that is what the 1960s was. Obviously in the 1970s surface based models were developed because the need was felt, for example for complex topology or surfaces, how a representation can be done in terms of numerical data or coordinate data. So a higher level CAD evolved where not only the edges but the surface became a very prominent application, and it evolved the surface data for boundary representations, although even this was again not very sufficient to represent a solid volume enclosure, okay, or for example informations related to what would be the volume of the particular object if it is not a regular object cannot be just had by looking into only the surface data or the edge data. So there were other versions which evolved over time, and there were a great many modifications which happened over the 70s, 80s and 90s. And you can see that from the 2D drafting to the wireframe design to the solid and surface and the solid modeling, and then finally the assembly modeling, which means that if you have two such solid objects, can I combine them together and contain them within a certain volume that we are looking at. And then finally parametric modeling and knowledge based engineering, which I am going to mention just about in a few minutes, started evolving with time. So typically all the way up to assembly modeling from 2D drafting can be categorized as geometry based modeling, and then these two other quantities which are, or two other forms of drafting which is called parametric modeling or knowledge based engineering, they are more like rule based, okay, and obviously they involve particularly the last step which is the knowledge based engineering, they involve a lot of intelligent processes like not only just the geometry or just the volume or just the design, but the finite element modeling aspect, the process simulations for some physical phenomena associated with the design that you are mapping, and again the complete design for manufacturing, and also a very important design optimization. So this is basically an intelligent thinking system which has now evolved, and nowadays all the software which comes in the CAD area are really process knowledge based engineering. With that approach you basically start all the engineering or design engineering. So as I told you that up till 70s when the surface based models were still not very sufficient, and the question of how to map two objects together or interconnect two objects together did not exist, there would be a sort of an emergence of the assembly modeling approach. All the solid modeling schemes do have an inherent weakness in that they provide a low level representation of parts in terms of only geometric and topological data constituting the model, okay. And as I told you, the finally emerged knowledge based engineering system not only includes only the design, but also the rules based designing, particularly the engineering rules based designing, like what kind of tolerances are there, what kind of part dependencies are there between the different let us say surface finishes of the different structures which you are trying to assemble, so on and so forth. So these are not related to really geometry, but some process rules which govern the designing process, but then that is the modern way or modern approach of doing all product design. So that is a sort of a historical perspective to design. Let us look at the manufacturing part. So modern manufacturing, if you can just split up into, is really a series of interrelated activities and operations, and that can involve, let us say, design, that can involve material selection, planning, production, quality assurance, management, marketing of discrete consumer and durable goods, so on and so forth. So there is a huge scope that there has to be a synergism between the various wings that have been mentioned right about now within an enterprise for a successful production in a modern manufacturing environment. There are some other attributes to modern manufacturing. One of them is the classification. You can classify manufacturing processes into continuous and discrete systems depending on the product line. Talking about manufacturing of oil and natural gas, or maybe production of something like sugar, it all necessitates a continuous production process. Now this course will not be intended for such systems. Mostly the course's focus more is on a unit by unit or discrete production system, what happens in an assembly line, and all the theorization that we will do in the following few lectures or modules will be related to mostly discrete processes, discrete production processes. However, modern manufacturing does include a very flexible attribute where you can combine mass production with job shop kind of production, and these systems therefore are also known as flexible manufacturing systems. There may be some processes which necessitate a continuous activity. For example, sheet rolling in a car making industry is a continuous process, okay, but then the moment it gets into a press shop and that sheet is pressed into different parts, it becomes a discretized process. So if you wanted to backwardly integrate at some point of time, you have to combine really the continuous flow production with the job shop kind of or the discretized kind of production systems, which will probably focus more on this along this course. Also the attribute of modern manufacturing systems are to a variety of modern tools which are available from the engineering technology side, which includes things like computer numeric control, which includes things like, let us say, automated guided vehicles with their different aspects, and also heavily relies on robotics and also group technology approaches, which eases out the manufacturing sequencing or the process sequencing in a manner so that you always tend to produce optimum yield in any business environment of any kind of pressure whatsoever. So these are some of the attributes related to modern manufacturing. Let us actually look at a little more historical perspective of how modern manufacturing had evolved, and the concept of a factory and productivity improvement is really attributed to this Adam Smith. He was a Scottish national, and he had this famous work on the division of labor entitled An Inquiry into the Nature and Causes of the Wealth of Nation. So this was one of the first treatises drafted in 1776 which talked about the modern day economics or capitalism and concepts related to how manufacturing would augment such economic systems within the world. So following this, in 1913 the manufacturing really had to see the day in about next probably 2 centuries. So a giant leap towards the modern day so called manufacturing happened in United States when Henry Ford for the first time introduced the first concept of assembly line, okay. So this was in relation to domestic cars, and this was one of the first initiatives where people realized how important it is when you chain up the sequence of process in a complex engineering object like, let us say, a product like car, so that you have the zeal and enthusiasm to keep producing on a mass production basis on a unit by unit basis these technology products. There were some other philosophers like Frank Gilbreth and Henry Gantt, okay. They developed the concepts of motion study and elimination of wasteful motion. So this was a ice on the cake of what Henry Ford had developed earlier. In an assembly line there is a continuous use of skilled expertise of a variety of people at a certain rate, okay, and there is always something called wasteful activities or non-value added activities which will happen in the process of the assembly. For example, in a car assembly there may be a tendency of all the people to do their job in a manner which they probably do not realize because that is the easiest approach that they have, but they are doing a lot more than what they should have done, okay. So there is a philosophy that in an engineering way or in a very logical manner, if you can observe the motion sequence of a particular operator associated with an assembly line and then try to identify those areas which are really non-value adding in nature and eliminate them in a way so that he does not feel any uncomfortable situation, in that case you can save a lot of time. So basically these Frank Gilbreth and Henry Gantt were two such people who were associated with some of these elimination of wasteful motions, and also a systematic graphing or a planning approach, so that you can always have the bottlenecks of a manufacturing process in terms of the most critical and the least critical. So then also things like related to scheduling of the activities, or related to let us say the progress review, or regular updating of data related to the manufacturing process in a very easy manner can it be represented, so that everybody around can have knowledge about the manufacturing process itself without really having to go into the depth of the process. Okay, so these two were really very good value additions again to the modern day manufacturing. And then obviously the breakthrough which was done by G.C. Duvall can be taken as again a very important historical step towards modern day manufacturing, who developed a controller device in the year 1946 that could record electrical signals magnetically and play them back to operate a mechanical machine. So this actually was the advent of the computer assisted machining systems, which later on emerged as the highly technologically most advanced domain of so called computer numeric control machines. Okay, so this is the way that modern day manufacturing kind of evolved from the very first work in 1776 all the way to the current the last century. And obviously there were some great breakthroughs which were made after this controller device was launched. One of them was the first numerical control machine which was developed at MIT under a subcontract from the Parsons Corporation, Michigan, on Air Force funding in 1950. There was also the development of automatic tool changers and indexing work tables that were added to the CNC machine in 1960, and then it started an era of manufacturing. The people started talking about integrating such numerical control machines into a one particular industry or one particular area where they would have a direct control of a central processor governing many such NC or numerical control machines. So there would be one processor which would be governing more than one numerical control machine. Okay, so the control system development in 1971 was again the next milestone, which led to the development of the microcontroller controlled NC, so called CNC, or the localized or the globalized control by the direct numerical controlling system or software, again merged into a manner so that you can have now the control at the local level of the machine without that global monitoring or global computing being required anymore. And nowadays the whole integrated one machining unit would have one controller of its own, and that controller can be linked to some other master controllers which would control, but then the processing capability, the intelligence capability are all now sort of synchronized with a particular machine tool rather than the global system of machine tools that was before in the DNC setup. So a major advantage of CNC machine is its ability to store part programs, also interact with controllers or central computers, as I just told, and the power of NC machines were further enhanced in 1980 by making them capable of carrying hundreds of tools, having multiple spindles, controlling movements up to 6 axes, so on and so forth, so that very complex parts could be produced. So I think this is a sort of an evolution process of how modern day manufacturing has evolved. There are many other systems which have been added to the manufacturing, like very good material handling systems, very good automated robotic systems, which would always assist in optimizing the existing manufacturing rate with lesser and lesser inputs. So we would like to conclude this module at this particular stage and start with the next, looking at some of the fundamental material handling systems, etc., and start with some basic CAD in the next module. Thank you.